Welcome to G Fun Facts Online. Today we're journeying to a hidden world, one that exists right here on Earth, but is concealed beneath kilometers of solid ice. Imagine a vast, dark network of rivers, streams, and enormous lakes, all flowing in constant motion between the base of our planet's great ice sheets and the rock below. This is the subglacial plumbing system, and it's not just a geological curiosity. This hidden hydrology is a powerful engine that controls the speed of glaciers, influences global sea levels, affects ocean currents, and even harbors unique ecosystems cut off from the rest of the world for millennia. To understand the future of our planet's ice, we have to uncover the secrets of this great, unseen water world. So how is it even possible for liquid water to exist under miles of ice, where temperatures are permanently below freezing? The answer involves a delicate balance of immense pressure and two key sources of heat. The first source is the surface. During the brief polar summer, meltwater can form lakes and rivers on top of the ice. This water is relentless, seeking out weaknesses. It plunges into deep cracks called crevasses and giant vertical shafts called moulins, some of which can be hundreds of meters deep, providing a direct pipeline for surface water to reach the glacier's bed. The second source comes from the bottom of the glacier itself, a process called basal melting. The sheer weight of the overlying ice, which can be thousands of meters thick, creates such intense pressure that it actually lowers the melting point of water. Add to this the natural geothermal heat radiating up from the Earth's crust, and the friction generated as the massive glacier grinds against the bedrock, and you have enough energy to continuously melt the base of the ice. But this water doesn't just sit there. It's forced to move, not by gravity as we typically think of it, but by pressure gradients. The immense, uneven weight of the ice creates areas of high and low pressure at the base, squeezing the water through a complex network of conduits, sometimes forcing it to flow uphill against the slope of the bedrock. This subglacial drainage system isn't uniform. It generally takes one of two forms, and the difference between them has huge consequences. First, there's the distributed system. Picture a thin, interconnected film of water spread out across the glacier's base, or a complex web of tiny, inefficient channels. Think of it like a swampy, slow-draining marshland. Because the water can't escape quickly, pressure builds up. This high water pressure can actually lift the glacier slightly, reducing friction and allowing the entire sheet of ice to slide more rapidly. This type of system is often dominant in winter, when meltwater input is low and steady. The second type is the channelized system. As meltwater input increases, especially during the summer, the slow-moving distributed system can evolve. The flowing water can carve large, efficient tunnels into the underside of the ice, some as big as subway tunnels. These are like subterranean rivers, capable of transporting enormous volumes of water very quickly towards the ocean. Because they drain water so efficiently, the water pressure within these channels drops. This increases the friction between the ice and the bedrock, which can actually slow the glacier's forward march. The dynamic switch between these two systems can happen over just a few days or weeks, causing significant seasonal speedups and slowdowns in glacier movement. Given that this entire system is hidden under miles of ice, you might be wondering how scientists can possibly study it. It's a monumental challenge, but over the years, they've developed a suite of ingenious tools. One of the most powerful is ice-penetrating radar. By sending radio waves from a plane or a sled down through the ice and analyzing the echoes that bounce back, scientists can map the topography of the bedrock, measure the ice's thickness, and, most importantly, find water. To a radar, a subglacial lake appears as a distinctively bright and perfectly flat reflector, standing out clearly from the rougher signal of rock. Similarly, seismic reflection uses sound waves to get a picture of what's underneath. The way these waves reflect can tell researchers whether the bed is hard rock or soft, water-saturated sediment. Scientists also look to the skies. Satellites equipped with incredibly precise laser altimeters can measure the surface elevation of the ice sheets. When a large subglacial lake fills or drains, the ice surface above it can rise or fall by several meters. These subtle changes are easily detectable from space, and this technique has allowed scientists to discover and monitor hundreds of active subglacial lakes across Antarctica. Of course, the most direct method is to drill. Using massive hot water drills, research teams can melt a borehole straight through the ice down to the bed. This gives them a direct window into the subglacial world. They can lower instruments to measure water pressure and temperature, and they can collect water and sediment samples to study their chemistry and search for life. They even use tracer dyes, pouring a harmless fluorescent dye into a moulin on the surface, and then waiting for it to appear at the glacier's snout. The time it takes for the dye to travel through the system reveals how efficient and interconnected the hidden river network really is. All this research points to a central fact. Subglacial water is the primary lubricant for the world's ice sheets. It dictates how fast they move, and therefore how much they contribute to sea level rise. As we've learned, high water pressure in a distributed system acts like a hydraulic jack, lifting the ice and allowing it to accelerate. This is often seen in the spring as the first pulse of meltwater reaches the bed. But as summer progresses and an efficient, channelized river system forms, the pressure can drop, increasing friction and causing a slowdown. This means that, counterintuitively, more melting doesn't always equal a faster glacier. In Antarctica, where surface melting is less common, the filling and draining of huge subglacial lakes is a major driver of ice dynamics. The drainage of one lake system beneath Bird Glacier, for instance, was linked to a 10% increase in the glacier speed that lasted for more than a year. The influence of this hidden water extends far beyond the ice itself, with profound consequences for the entire planet. The fresh water that flows through these subglacial systems eventually pours into the ocean, and this has a massive impact on the stability of ice shelves. The enormous floating extensions of glaciers that fringe Antarctica and Greenland. Because fresh water is less dense than salt water, it creates buoyant plumes that rise up along the face of the ice shelf. This process sucks in warmer, deeper ocean water, bringing it into direct contact with the base of the ice. This dramatically enhances melting right at the grounding line, the critical point where the glacier begins to float. This melting thins the ice shelves, weakening them and reducing their ability to act as a dam, holding back the glaciers behind them. The result is an accelerated flow of ice into the ocean, which directly contributes to global sea level rise. In fact, some models suggest that including the effects of subglacial discharge could accelerate the retreat of major glaciers in East Antarctica by as much as 25 years. This massive influx of cold, fresh water can also disrupt global ocean circulation patterns, like the Atlantic Meridional Overturning Circulation, or AMOC. This is the Great Ocean Conveyor Belt that transports heat around the globe and regulates our climate. A slowdown of the AMOC, which has been observed in recent decades, can trigger complex and widespread changes in weather patterns worldwide. Perhaps one of the most astonishing discoveries is that these dark, cold, high-pressure environments are not lifeless. For a long time, the world beneath the ice was assumed to be sterile, but the exploration of subglacial lakes has revealed a hidden biosphere. These environments are home to diverse microbial communities that have been isolated from the outside world for thousands, even millions of years. Without sunlight for photosynthesis, these microbes are chemosynthetic. They derive their energy from chemical reactions with minerals and compounds found in the water and sediment. The constant grinding of the glacier on the bedrock creates a fine, chemically reactive rock flour that provides a steady source of nutrients. These bizarre ecosystems are a subject of intense interest for astrobiologists, as they serve as an analog for potential life on other icy worlds in our solar system, like Jupiter's moon Europa or Saturn's moon Enceladus. While the day-to-day workings of this system are gradual, sometimes the plumbing bursts with terrifying power. These events are called glacial outburst floods, or by their Icelandic name, jökulhlaups. They can be triggered when a large subglacial lake suddenly drains, or when a volcano erupts beneath an ice cap, generating a colossal amount of meltwater in a short time. The 1996 eruption under the Vatnajökull ice cap in Iceland triggered a Jökullaup with a peak flow rate comparable to the Amazon River, unleashing a torrent of water that carried house-sized icebergs and demolished bridges. More recently, in an even more surprising discovery, scientists observed a subglacial flood in Greenland that burst upwards, fracturing the ice sheet from below and creating a massive crater on the surface. As our planet warms, the amount of surface meltwater pouring into these subglacial systems is projected to increase dramatically, especially in Greenland. The consequences are complex. An initial pulse of water might cause glaciers to speed up, but the long-term development of more efficient drainage channels could potentially slow them down. However, what is certain is that the increased discharge of fresh water into our oceans will continue to accelerate the melting of critical ice shelves and push sea levels higher. Unraveling the secrets of the hidden rivers beneath the ice is one of the most critical frontiers in climate science. It's not just about exploring a hidden world, it's about understanding a key driver of our planet's future.